Hello. As you may know or imagine, most algorithms used to train neural networks are based on some sort of gradient descent. In this lecture, we introduce gradient descent with momentum, which is a variant of gradient descent that almost always speed ups the performance compared to standard gradient descent. Before introducing momentum, we start by revisiting the concept of convex function, which is intuitively a function with a U-shape. More formally, we say that a function is convex if the line segment between any 2 points of the graph of the function lies above the graph between the 2 points. Convex functions are particularly important in optimization because they are particularly nice to optimize. In fact, any local minimum of a convex function is global. Furthermore, convex functions are closed under summation and maximization, which makes them particularly nice functions to deal with. As any local minimum of a convex function is global, it means that convex function can be minimized by first-order optimization algorithms such as gradient descent. In particular, gradient descent is an optimization algorithm that aims to find the local minimum of a function starting from a given point by taking small steps in opposite directions of the gradient. Recall that the gradient of a function in a point represents the direction of growth of a function in that point. Therefore, moving against the gradient will locally minimize the function. In gradient descent, as we can see in the slide, at each iteration the current minimum is updated with the gradient of the function times a parameter called the learning rate. At each iteration, the learning rate determines the size of the step that we take. Intuitively, a small learning rate means a lot of iteration of gradient descent to converge to a minimum, while a large learning rate can speed up convergence. However, if the learning rate is too big, it can lead to oscillation and even divergent behavior, which is when the gradient descent does not converge to a minimum. In this context, momentum is a modification of the gradient descent algorithm that allows us to take large learning rates while still converging. Intuitively, we would like to reduce the zigzag behavior that we observe in the picture on the left. This implies reducing the gradient in the vertical direction. At the same time, we would like to also increase the horizontal gradient, as that would mean faster convergence. If you think about it, you can see that a way to do that is simply to sum the current and past gradients at each iteration of the gradient descent. In fact, if we take consecutive gradients, these will have opposite gradients in the vertical directions, and same in the horizontal one. So, if we sum current and past gradients, ideally we can obtain a much better direction with reduced zigzag behavior. Smaller magnitude in the vertical, which means smaller magnitude in the vertical gradients, and faster convergence, which means increased magnitude in the horizontal direction. This is exactly what momentum does. The current gradient is summed to the previous one multiplied by a constant called momentum, which indicates how much we should consider the previous gradient. Then the gradient descent algorithm proceeds as normal with the modified gradient. As discussed, momentum has a smoothing effect as it cancels out gradient direction that disagree. It also has an amplifying effect. If successive gradients point in a similar directions, we go faster in that direction.